Okay, thank you very much. Thanks everyone, and thanks for sticking it out through an excellent session today. I am going to move into dangerous territory for a room full of spectroscopists, which is beyond the several top centimeters of the lunar surface, into the deeper subsurface, and talk about how we can use physics to understand processes that are going on there. So if there are operational or industrial deposits of ice on the moon, they're very likely in the deeper meters, tens, hundreds of meters of the subsurface where they may be long-lived. And so to prospect for them, we need to use the same tools that we use to prospect for resources in the subsurface on the Earth. Those geophysical tools are things like seismic, GPR, electromagnetic methods, and to interpret the data from geophysical surveys like that, we need to have an understanding of the physics of different materials. I'm going to specifically be talking about seismic rock physics today. And in order to interpret seismic data on the Earth, we use rock physical models. And in particular, I'm going to be talking a little bit about effective medium models, how we understand the behavior of composite materials, which is what an icy regolith material would like. And to use the right model, you need to really understand the physical properties of the components and also the microstructure. You can sort of imagine how you might have a sort of ice-supported microstructure or a grain-supported microstructure, or something that is more complicated. And these all have associated mathematical models that can relate the microstructure and the properties of the various constituent parts to an effective property, which is what you would be measuring using seismic methods. And so here is a sort of compilation of a number of these different rock physics models using dry and ice-filled regolith as end members. And as you can see, if we want to understand the difference between 1% and 90% of ice in the pore space of there, we need to really understand what the microstructure of those icy deposits and the associated regolith is. To approach this, we have been doing X-ray microtomography experiments using a cell that is engineered to recreate lunar surface conditions. So very cold, high vacuum conditions. Here's a picture of our cell in its sort of beta version, sitting on the X-ray beamline at the Advanced Light Source at Berkeley National Lab, which is a synchrotron user facility that we make these measurements at. And what is great about these measurements is that they give us really, really good high fidelity pictures of the microstructure of the sample. So this sample here is one of the commonly used analogs. This is JSC1A. It's a basalt from Arizona, but spectroscopically it is similar to certain areas of the lunar surface. And as you can see, it has a really interesting, complex microstructure. So the grayscale here is roughly proportional to density. The darker bits are glassy matrix, the lighter bits are crystallites, and here highlighted in red are the internal pores that exist within this rock. So we can use this data to examine the internal porosity, the external porosity, the grain contracts, the geometry of the various things. And we can actually use this to understand the coordination of the grains and then make the sort of a best judgment about what kind of physical models we ought to be using in order to describe the behavior. So we've been looking at not only dry versions of this material, but various sample preparations to look at how ice can sit in the pore space. These are just 3 examples of sort of a fully ice-filled pore space, a partially ice-filled pore space, a like sparse microstructure that is partially grain-supported, partially ice-supported, and extremely heterogeneous. We can look exactly at the ice. We can look exactly at the grains. Using this information, we've picked our most appropriate rock physics model. In this case happens to be a modified Hashine-Strickman model, and then measurements of the elastic properties of these grain packs that we do ultrasonically in the lab, and we can use that information to make these velocity models that relate ice fraction in the pore space to a seismic velocity that you'd measure in the field. We then take real data from the moon. So here is a thermal model of the south pole of the moon. to look at what the temperature structure would very likely be, where you have these cold zones in the permanently shaded craters and sort of halos of dark regions and warmer regions in between there. We use that information to populate different envisionings of how ice content might sit in a region like that. Maybe you have massive ice that sits only in the permanently shaded regions. Maybe you have massive ice with sort of halos of disseminated ice in the other cold regions. Maybe you only have disseminated ice, or maybe you're really restricted to having disseminated ice just in the very darkest and coldest regions. We then take this data and run synthetic seismic experiments. So here we have an experiment that's run with 81 seismic stations every 100 meters through the center of our model, and a source that's sort of right in the middle. And then we can look at what a real seismic experiment on the moon might look like. Here is an example of what the surface wave field would look like at a time step 25 seconds into the simulation. And you can see that the regions here where we have the ice-filled craters are blocking a lot of that seismic energy. And if we look sort of closer into cross sections. So here in this, I call this the wishful thinking model, where we have massive ice in the craters and ice emanating outward into the cold shadows. You get some really interesting effects. You can see that we have the waves that are diffracting off the corner of the massive ice bodies, and other interesting scattering effects that take place in the sort of disseminated ice halos. But even if you look at our most conservative model, where you just have sort of small amounts of disseminated ice that exist in the permanently shaded regions, you still have a lot of scattering effects that you can observe. And what we're trying to demonstrate using this sort of approach is how seismic methods can potentially be a really powerful tool for prospecting for these sort of ice resources on the lunar surface. And using this sort of approach, we can really pick apart sensitivities, design seismic experiments, and other sort of geophysical methods to take a really close look at these things. So yeah, I went through a lot really fast, so happy to take questions.
This might not be the right direction, but what if it's not water ice?
Well, then it'll have different physical properties, and those can be incorporated into the rock physics model as well. So I didn't include the actual models up here, but the physical properties of the various constituents of the effective medium play roles in there as well. And the reason that we designed our microtomography cell to be able to reach those conditions is so that we can actually do some of the physical property characterization. We can do elastic measurements while imaging, so that we can make robust correlations between the microstructure and the physical properties of the different materials. Yeah.
I'm just kind of curious about the scale of this and how, like, at what scale does that change in ice fractions start really mattering? Like, is it like centimeter blocks that are changing, or do you have to have like a mass, like a meter by a meter of a certain kind of porosity?
There's a size for frequency trade-off. So depending on what frequency seismic data you're looking at or measurements you're applying, that actually is going to be sensitive to different length scales of microstructure. So yeah, it sort of depends specifically on what it is that you're addressing. But that in fact gives us other tools to look at the frequency dependence of the seismic response and perhaps get some more information about length scales as well. Okay, anything online? All right, well, with that, thank me one more time. And we can move on to the discussion portion of the show. So I think most of our speakers are still around. So if anybody has any questions that we didn't get an opportunity to address, then this is our opportunity. And if everybody's just really hungry, then we can thank all the speakers one more time. And Tom, you got something?
I have one on your talk.
Okay.
Really like, so the water, where it goes in this rain is, sort of unclear, but, once it gets in pour, it kind of wants to stay. So do you have a feeling on sort of, what is like you know, the hiding places, and then what is the minimum amount of water you're going to have some effect on this dielectric property?
Yeah, I mean, it's a great question, and I think that the answer can be found through these sort of methods where we can actually, so these different ice microstructures were made via different sample preparation techniques, none of which are probably realistic to the way that ice is deposited in the lunar regolith. So doing those measurements, like doing some real vapor deposition and transport, thermal aging, all that kind of stuff that's more realistic to the way that volatiles are probably behaving, and then doing these measurements will give us an idea of what the most likely places that they are. You know, right now we're sort of doing best efforts to like look at a spectrum of where the ice might be sitting, but where it actually is sitting is totally relevant information. And so, yeah, I think that needs to be a direction we go.
Fascinating modeling that you've done to. And have you thought about how it might apply to the insight data on Mars, and think about if there's an ice regolith or something that.
Boy, have I. The Martian hydrogeology is a lot more interesting than lunar hydrogeology. So a lot of the techniques that I'm using here are techniques that have been honed and developed through studying permafrost, terrestrial permafrost. And some of the interesting rock physics effects that take place in terrestrial permafrost are sort of freezing point depression and small grains. So when you have clay, which is likely in the Martian regolith in some regions, that adds a layer of complexity. If you have saline pore fluids, which is likely the case in the Martian regolith, that adds another layer of complexity. Those are all effects. Those are actually, because there's all those additional layers of complexity, it actually means that we can use these techniques to get sort of more robust information about the behavior in a place like Mars. But, you know, very few of those measurements have been made yet. And yeah, the work hasn't been done, but there's a lot of really interesting directions. And I'd love to talk more about it because I think about it a lot.
So you say you need to develop the algorithms to put them onto a Martian environment?
Well, cards on the table. I'm an experimentalist myself, and I think we need some more measurements. The models are pretty good. But the parameterizing of the models is fairly unconstrained right now. So I think that those measurements would be a great place to start, and then we can make some predictions, and then we need to get more seismic instruments on Mars.